Now, when we balance the amount of electrons transferred in a redox reaction, what we're really doing is ensuring that the law of conservation of charge is still holding place. And what that means is that the amount of electrons that you begin with when reactants combine must be equal to the amount of electrons that are transferred or that you end with in the products once the reaction has ceased. Now, how does the conservation of charge lead to conservation of mass? Why does balancing the charges in redox reaction lead to balancing the atoms and essentially the entire redox reaction in totality? Well, the answer is subtle, but it is sensible. Now, electrons can be either a particle or a wave, and sometimes both at the same time. And so that makes it difficult to really track any kind of mass deficit or to account for any of the electrons' masses at all, really. However, the majority of the mass of an atom is centered in the nucleus, which is comprised of neutrons and protons. And so when an electron is transferred from one atom to the next, if the charges aren't balanced, then you're going to have to need more protons for that compound that got the electron transferred to it in order for it to be electrically stable. And if there's one thing that matter doesn't like, it's to be unstable in any way, specifically to be electrically or electrostatically unstable. So in short, if the charges are balanced, that means that the electron transfer is balanced on both sides of the equation, and hence there isn't a need for more protons or more nuclei, which is the majority of the mass of an atom. And so if the charges are balanced, then by default, the mass is going to be balanced as well. Now, before we begin the process, we have to identify that what we are indeed looking at is a redox reaction. And so remember that redox reactions involve changes in the oxidation numbers. If there are no changes in the oxidation numbers, then it's not a redox reaction. It could be another type of reaction, like a double replacement, but not a redox. If there's a substance that increases in oxidation number or becomes more positive from reactants to products, then it's losing electrons and hence oxidation is taking place. If, on the other hand, you notice a decrease in oxidation number where the substance becomes more negative or less positive from reactants to products, then that substance is likely gaining electrons and there's reduction taking place. Remember that both of these have to occur in order for this to be a redox reaction. Once you've confirmed through assigning oxidation numbers that both are occurring, then you start the balancing process using oxidation numbers. So for this reaction here that occurs in an acidic medium, copper plus nitric acid yields to copper 2 nitrate plus nitrogen monoxide plus water. The first thing we're going to do is assign oxidation numbers using the rules that we talked about in the previous video class. The next step we're going to do is we're going to identify which substance is being oxidized and which one is being reduced. And we're going to do that by tracking the changes in oxidation numbers. So if we look here, again, I'm only looking at changes per atom. And that's very important to state that it's per atom. None of these in brackets are the totals that we're looking at. So if I look at copper, it goes from 0 to 2 plus over here. And so if copper is going from 0 to plus 2, then that means that it loses 2 electrons. And so that undergoes oxidation. Now for the second change in oxidation number, if I look at the nitrogen goes from plus 5 to plus 5, well, that's not a change, but the nitrogen from here to here undergoes a decrease in oxidation number. It actually decreases by 3. So if the nitrogen goes from plus 5 all the way to 2, then that must have gained 3 electrons. And so the nitrogen undergoes reduction. given that the copper got oxidized and the nitrogen reduced, then that makes the copper the reducing agent because it causes something else to get reduced by getting oxidized itself. And then the nitrogen is the oxidizing agent for the same reason that it causes the copper to get oxidized by getting reduced itself. The next thing we're going to do is balance the electrons, or I could say the electron transfer. And what we mean is that the electron loss has to equal the electron gain. And the way we're going to do that is we're going to find the least common multiple between the amount lost and the amount gained. In this case, the LCM of 2 and 3 is 6. And so to correct that, what we're going to do is we're going to add a coefficient in front of each of the substances that are undergoing that electron transfer change or that oxidation number change. So since copper goes from 0 to 2 plus, we're going to have to multiply this one by 3. And so we're going to take that multiplier and put it as a coefficient in front of the coppers like so. And then for the nitrogen, which gains 3 electrons, in order to get it to equal to 6, we're going to multiply it by 2. So that multiple or that multiplier is going to go in front of the nitrogens, specifically where there's an electron transfer or an oxidation number change. And what these coefficients essentially do is they begin the balancing process. Now, they might change later on, but they definitely get us started, especially for the next step. Now, another thing that I want to point out is that this lowest common multiple of 6, what that means is that there's a total of 6 electrons transferred in this reaction, right? In chemistry, there is no number that is meaningless. Nothing happens for no reason. These lowest common multiples that we just found tells us how many electrons need to be transferred in order for this reaction to be successful. Now we're going to combine and balance the rest of the atoms that are not hydrogen and oxygen the same way we would normally balance a chemical reaction. So we're going to start with copper here. There's 3 coppers on this side and 3 on this side, so that checks out. That's good. Let's look at the other non-hydrogen and oxygen atom, which is nitrogen. So there are 2 nitrogens right now with the coefficient, and there's 3 times 2 nitrogen, which is 6, and then plus 2 over here, that's 8 nitrogens on the product side. So we're going to have to change that coefficient of 2 here to a coefficient of 8. And so when I rewrite this, that is going to be 3 copper plus 8 HNO3, which yields to 3 copper 2 ditrate plus 2 nitrogen monoxide plus water. And then finally, we're going to balance the oxygens by adding water, and then balance the hydrogens by adding H+, and we're going to add the appropriate amount to the deficient side. So if I'm going to start with oxygen first, I got 8 times 3, that's 24 oxygens on this side here. And then for the product side, I got 3 times 3 times 2, that gives me 18 oxygen plus 2 times 1, that's 2 plus 1. So that gives me a total of 21 oxygen. So we're going to have to add 3 waters to the product side. So if I rewrite this reaction, it'll be 3Cu plus 8HNO3 plus 3Cu NO3 plus 2NO. And then if I adding 3 H2O here, and I already have 1 H2O, I can change that to just 4 H2O, combine like terms. And then we're going to add, or we're going to figure out how many hydrogens we need to add, H plus to the appropriate side based on the amount that are already present. So we got 8 hydrogen over here. So I got 8 H plus And then here we have 8 hydrogens as well here. And so given that they're equal on both sides, there's no reason to add H plus to either side. So this would be the final balanced redox reaction. A quick way that you can tell if you've done this right is when you calculate the total charge on each side, they should also be equal as well, because remember, redox reactions have to balance in mass and in charge. And for this question here, you could see that they both have a total charge of 0 on each side, meaning that, this was done correctly. So zinc is reacted with hydrochloric acid to yield zinc chloride and hydrogen gas. If this is a redox reaction that occurs in an acidic environment, I want you to use the same rules that we used in the previous example to try and balance this one on your own. And if you use the same rules in the same order, it should work out. Pause the video and give it a try. Now, when we have redox reactions that occur in a basic environment, the process is largely the same, except at the end, we do want to neutralize those H plus ions. So basic solutions contain excess hydroxide ions instead of the H plus ions, and of course, we're talking in the final solution. So you're still going to follow the exact same oxidation number method, but like I said, there'll be one key difference. After you balance the H plus and the H2O, you're going to neutralize the H plus ions by adding OH to both sides. And this is identical to what we did when we were using the half reaction method for balancing. And remember that every time you add OH minus to a side that has H plus already, it makes a water molecule. And that's because they neutralize each other. The first thing we're going to do is we're going to assign oxidation numbers to each element inside this reaction according to the rules of assigning oxidation numbers. The next thing we're going to do is we're going to identify which element is getting oxidized and which one is getting reduced. And we can see that the manganese gains 3 electrons, and that the iodine is going to lose 1 electron per atom. And since there's 2 atoms of iodine on the product side, in total it's going to lose 2 electrons. Now we're going to ensure that the electron gain is equal to the electron lost by finding a lowest common multiple between 2 and 3. In this case, that would be 6. And so the multipliers of 2 will be attributed to the manganese, and the multipliers of 3 will be attributed to the iodine. Next, we're going to balance all the non-oxygen and non-hydrogen atoms, and in this case, since the manganese are already balanced, that leaves us just with the iodine to balance, and putting a 6 in front of iodine minus, or iodide, would balance that. Next, we're going to balance the oxygens by adding water to the appropriate side. So if the reactant side has 8 oxygens and the product side has 4, that means we need to add 4 waters to the product side. After that, we're going to balance the hydrogen by adding 8 H pluses on the reactant side. And since this is a basic solution, we're going to add 8 OH to cancel out that 8 H plus on both sides. And remember that 8 H plus and 8 OH minus result in 8 waters on the reactant side. Now we're going to simplify this redox reaction by canceling out any like terms on each side, which in this case would be the waters. So the 8 would reduce to 4 for the reactant side, and then the 4 waters would be just eliminated, and that would give us this final balanced redox reaction.